All right, everybody, this is a video on the hmrMotionCorrectSpline function. As you can see, it's the hmrMotionCorrectSpline. It's basically a motion correction algorithm that is implemented in Homer 2, allows you to correct for various types of motion artifacts. It's one of like 7 or 8 different options that you have. So it's not the only one out there, but I'm going to explain kind of how it works and show you how to put it into a pipeline to use it. So the function has a couple prerequisites. One of the prerequisites is optical density. So your data typically comes in like a raw voltage format, and most of the functions within Homer 2 actually expect the data to be in optical density. So what this means is that you actually have to run, initially you're going to have to run the HMR intensity to OD function. This is going to take your data, create a zero mean of the data, and take the negative log change. And that's now your optical density. It's a unitless aspect, and it gives you the relative change for FNIRS. In addition to altering your data from raw intensity to optical density, you're also going to have to include a variable called the tinc, which stands for time included. And this is actually, it's not something you have to create or anything, but you will have to run a function to output it. That function is the HMR motion artifact by channel. And what this does is actually locate motion artifacts. Based on a few parameters, it'll actually tell you, okay, this is a motion artifact, here's a motion artifact, but it doesn't actually correct for them. What it does is give you an array of ones and zeros indicating that all the ones are good. At the 0 points, you're going to have to correct for them. If you don't have those, you may get I think you will get an error in running the spline correction. All of the input variables are as follows. So you have, as mentioned, the delta optical density, which is basically the data being put in. The time vector, which is it's already in the background of your .NIRS file, but it does have to be there. The SD structure, again, it should be in the .NIRS file, at least the upgraded or updated conversion scripts will include it. It includes all the information about your sources and detectors, so XYZ components, I believe the connections and channels between them. And then finally, as mentioned, the tinc variable, which is made by the motion artifact by channel. The only variable that you're actually going to manipulate yourself manually is going to be this p variable. This parameter is actually put into the spline interpolation, and the default value is 0.99. If you use a value of -1, it will actually omit the function, so it just ignores the spline correction. The only reason I could see that anyone would want to use this is if you have a pipeline and you run it and you get the spline correction, you want to compare it against not running the spline correction, and you don't want to write a whole new pipeline. So you just put in -1 and you can see the difference. This p value itself, though, is kind of curious, but I kind of think of it as what % of your motion artifact do you want to model and remove? So if it's at 1, you're modeling and removing essentially your entire motion artifact. If it's 0, you're really not removing anything. And 0.99, you're removing quite a bit. You're assuming that the motion artifact is predominantly motion. And you have wiggle room all between that. And I'll actually show you what the differences look like. The output of this function is going to be the same exact format of your data that you started with, which is delta optical density. But it's going to be corrected. So now you've actually taken those time included segments that you stated, this is a motion artifact, here's a motion artifact. You've corrected for it, and you've output the new data. This is what it would look like if you were implementing a pipeline. So first step, you're going to convert everything to optical density. That's almost the first step regardless of what you're doing. Next, you're going to identify all the motion artifacts. The input to these are T-motion, which basically says I'm going to look for a certain width of a window, and within that window, I'm going to look for a set amount of change. If it changes by some threshold value that I designate, within that time frame, I'll mark it, and that will be my motion. If it's that same threshold, but it's over a longer time, it doesn't matter. I'll kind of ignore it. The next input is T-mask. T-mask is saying if I mark it as a motion artifact, how many seconds before and how many seconds after do I actually want to flag? Because ideally you have the motion artifact, but before and after is probably a little bit ugly too. So you want to correct within that. And it's set to 1 second. The next two input variables are actually kind of either or, in my opinion. The first one is standard deviation change. It's stdev thresh. So it's a threshold value set on standard deviation. And the second value is an amplitude threshold. I don't foresee why you would need to use both at the same time. I think, in my opinion, you use either standard deviation or amplitude, although maybe there's an application that I'm not aware of or a reason that I'm not aware of that one might want to use it. If you want to use one and not the other, you basically set the one you want to use to a reasonable value, and you set the other to a very unreasonable value, very, very high. And basically what that gives is the one you don't want to use is the threshold is so high that the value will never reach that, and therefore you'll just ignore it. So I like using standard deviation because it's standard. So it makes more sense to me. I set the value to 13 here because I'm looking at a time period, again, T-motion, of 0.5, which is half a second. I'm sampling at 8 hertz. That's about 4 samples. Well, each sample within reason could be roughly 3 standard deviations away. So 3 times 4 samples is 12, and I'm putting it 1 above that. So assuming that 12 is probably fine, anything above 13 is arguably questionable. So that's the reason I chose that. There's probably a very good argument to choose a different number, and maybe a very good argument for me for my reasoning of being incorrect. But I like the value of 13. I'm going to use that, and therefore I'm going to ignore amplitude threshold. I set a value of 100. Nothing of my data is going to be changing over 100. So I'm set there. So that marks my motion. The next thing I'm going to do is input my p-value, and I'm going to use the default of 0.99. This is what actually happens. So the first figure you see on the left is my motion artifact. I've zoomed in on it a lot, so it looks a little bit wider, but it's a motion artifact. And the middle image is actually the spline correction. And splines, just to give you a little historical background as to why they're called splines, they name them after the shipbuilders used these curved bars of wood called splines. So we're using these curves to fit the motion. And then now we've referred to them as splines. So it's not some strange mathematical term, it's a shipbuilding term. But if you can see it here, this is essentially my model of my motion. And you can kind of overlay it here. You could get a pretty good idea of its relatively good fit. Here is basically the residuals. So I fit my model to the data. I'm going to remove everything that's my model, and I'm going to keep the residuals. And you get an output similar to the one on the right. There's a lot of assumptions that go into that, but it's kind of an interesting fix. This is the first step. So that's kind of the overall process. Here's the first step of it. So first thing you're going to mark the motion. So here I've removed the spline from my pipeline. Let's see right here. I just have intensity to optical density, translate the data, and then I'm going to selectively locate the motion artifacts. And here's a motion artifact. Now again, I'm zoomed in on it. So here you see this nice big dip. I've marked it. Great. There's a motion artifact. Now I need to correct for it. So here I've used the same values that I had in the previous slide of 0.5 seconds. I'm looking for a half-second window. I'm going to mask everything 1 second after and 1 second before, and that's going to be my motion. I'm going to correct within that window. I'm looking for a standard deviation change of 13 or greater. I'm basically ignoring amplitude. I'm looking for an amplitude change of 100 greater. It's not going to find it. If you notice, the values over here are far less than 100. And then I use the standard 0.99 as my P input. So now I want to correct it. Oh, and I actually got ahead of myself. So I correct within here. So comparing this big drop here to this data, which actually maneuvered in such fashion. But you'll notice there's still this big drop here. So I've corrected it to some extent, but I still have a pretty nasty drop there. So and the other thing you'll notice here is now we have optical density, I believe, versus, oh no, excuse me, they're both optical density. So I've corrected for it, but I actually still have this nice drop here, which isn't ideal. I clearly didn't fix the whole motion artifact. So what I'm going to do here is change this mask to a little bit longer. I just jumped the gun and put 2 seconds. You probably want to be a little bit more explicit than I was in doing that, but I knew 2 seconds would cover. I threw 2 seconds in. So here we go. We throw it in, and there we go. We fixed a motion artifact. You can see it's not perfect by any means, but it doesn't look at all like it did before. There's no significant drop. It kind of continues along the mean. It was over a 2-second window, not a massive amount of time. Depends on really where you have it, but maybe that's a good version for your fix. So now I've selected my motion artifact. I've fixed my motion artifact to whatever extent you want to consider that. Now the question is, what happened? Did I pick the right values? Why would I choose 0.99 versus something else? So I'm going to show you what the differences are. So here's a p-value of 0. And basically what you're doing is this is a different motion artifact here. I think it gave a better example, so I selected this one. So you see kind of 2 jumps here. This is my original data. This is the model for the motion. Doesn't really make sense. It's a straight line. The output is identical to the input, except there's been a shift in the y-axis. So it basically shifted my values up by, what, 0.1, I think. So all that happened was there was a shift in the values. The motion's still there. They really didn't really do anything. So this is what a value of 0 gets you. If I have 2.5, gives you a little bit of a fix. So here you can see my original data. Here's my model, and you see it actually kind of fits the data right there. But then the output is still kind of motiony. I would say there's still 2 pretty significant cuts right there that don't look too trustworthy. It's a little better than before, but I wouldn't say much better. So we're going to go to 0.5. So here we go. Here's the original data again. I've added a little bit more of a flat line here. There's a little bit of a shift up here in the 2 minimums. And now you're seeing it's comparatively slightly less extreme. We're getting there. Still not great. Let's see what 0.75 gets us. Okay, so now you can actually start to see a mean here, right? Actually start to see a little bit of a mean value. There's some variation still present, but it's starting to kind of regulate in a way. And then finally, we have the default value. So the default value basically gives you very minor variation within the signal. And you see also the model here is actually quite similar to what we have here. It's almost just a smooth version. So we've gotten quite close with that. So that's the spline itself is kind of at least to me, it was a big mystery because it's called spline, and I didn't understand what the heck that meant. But the idea behind it is quite simple. It's just saying, okay, we're going to model the data, and we're going to do it with a fairly complex shape. Then we're going to look at the difference between the shape and the actual data. That difference, we can assume, is not the motion. Whether or not that assumption is right is questionable, but the idea is fairly simple. And what it gets you is a fairly useful tool to attack motion artifacts. But anyway, I hope that was helpful, and I hope it enables you to actually understand what you're doing and how to do it. And I'll keep posting up videos like this. Please give me some recommendations on any functions that you guys are interested in or having trouble with. Anyway, thank you guys.